Good afternoon, and today we are going to cover some specific topics related to confidence intervals that are not necessarily clearly covered in the textbook. Okay, so first of all, we are going to use a package which I don't know if you have downloaded and installed yet, but if you haven't, please do so. It's called HMISC, HMISC. Let me get the spelling of that right. Okay, so first we're going to call this package. We're going to read in our heart data once again. And so we're going to look at the confidence intervals around a binary variable, a yes-no variable, or a 0-1 variable, which we do encounter in one of the homework problems. Okay, and so the way that we calculate a confidence interval around this type of variable is a little bit different than how we calculate it around a continuous variable, which is what the lecture on June 25th covered. Okay, and so there's a variable in our heart data set called exercise-induced angina, and we can see from the unique function here that the values of that are 0 or 1, corresponding to yes or no. Okay, so this variable is suited for our question. And I'm going to run the sum function on this variable. That's going to tell me that there are 99 yeses, or 99 ones in the data. And we can see up here in the global environment, top right, that there's 303 observations in the data set. So in this data set of 303 patients, 99 had exercise-induced angina. And so there is a function in the HMISC package called binconf, so for binary confidence intervals, abbreviated. And it's pretty simple. You ask it to return the binary confidence intervals where you provide x is the number of yeses or successes, and n is the number of observations. So we have binconf, x equals 99, n equals 303. We run that, and we get a point estimate, which is 0.3267. So that's the percentage of patients who have this condition. It also corresponds to 99 divided by 303. Right, so about 33, about 1/3 of the patients in the sample have this condition. And so that's our point estimate. And we could, like I said, we could have just gotten that from 99 divided by 303. So that's not all that interesting. But what's interesting here is that we get the lower and upper confidence intervals from this without having to do a lot of typing in of formulas. And we see that the range, the 95% confidence interval range, is from 0.276 to 0.381, or 27.6% to 38.1%. So the way we interpret this is, and like I said, for the purposes of this class, we can take the simpler, more intuitive interpretation, which is not technically correct, but close enough for our purposes. We can say that in this sample of 303 patients, assuming the sample is representative of all the people in the world, or the United States, or whatever your reference population is, based on our sample, we could assume that while we saw 33% of the patients in our sample had this condition, in the entire population, we would expect that it could be anywhere from 28% to 38%. Okay, so that's our range of possibilities. So the confidence intervals are going to be surrounding the point estimate. And most of the time, they're going to be symmetrical around that point estimate, meaning the distance on the left is equal to the distance on the right, right? So 33 minus 28, that's about 5%, and 38 minus 33, that's about 5%. So we could also say that another way to interpret this result is to say that 33% of patients have exercise-induced angina, plus or minus 5%. Okay, that's how we would report that in a report or journal article. Okay, now that's how you deal with variables that are yes or no, 1 or 0. More often, and this is the example that we saw yesterday and the day before, more often we have data that are continuous. Okay, and there's a variable called maximum heart rate achieved in our data set, and if we look at the summary of that data, we can get a sense of, oh, I forgot to type the name of the data set, heart, $. Okay, so we see maximum heart rate achieved has a minimum of 71, a mean of 149.6, maximum of 202. So this is a continuous variable with a pretty wide range, and we're going to assume that it is normally distributed or close enough to normally distributed. Okay, and so when we do that, we can, there's another function called t.test. Now, t.test is built into R, so it's not part of HMISC. It's not part of any external package, it's built in. Okay, so t-test, and if you recall from the lecture, t-test is what we use when we have small samples. And you'd say, well, we have 303, that's a pretty big sample. We don't really need to use a t-test. It doesn't hurt to use a t-test. You have to use a t-test when your sample is small. But when your sample is large, you can still use a t-test. It gives you the same answer as a z-score based method. Okay. Okay, so all we have to do with the t.test function, t-test and the name of the variable that you're interested in, and the confidence level. So if we run this, we run line 11. So we get a bunch of output. It tells us there's a t statistic, which we don't need to worry about too much, but we just see that it has a value of 113.84. DF stands for degrees of freedom. We don't need to worry about that too much. P-value is something else that we're going to be learning more about these things going forward. What we care about for the moment is this confidence interval. Okay, so our 95% confidence interval goes from 147.0 to 152.2, a mean of 149.6. So if you do the subtraction, you'll see that the confidence intervals are equally spaced in both directions from the mean. So again, symmetrical distribution. So the way we would interpret this is that in our sample, our 95% confidence interval was 147 to 152.2, and if this sample is representative of the whole population, then we would say that we're 95% sure that the true value in the whole population is somewhere between 147 and 152.2. Okay, now, so this is a very easy thing to type. There's only one function, two parameters, and actually the confidence level equal to 0.95 is the default. So technically, you don't even need to type this unless you want a confidence interval that's other than 0.95. But nearly always in science we use 0.95. So if I run it without that 0.95 term, it still gives us the same answer because it's the default. Okay, so this is super easy to do, but in case we want to do it the somewhat longer way, we can use the formula that I showed you. The confidence intervals are the mean plus 1.96 times the standard deviation divided by the square root of the sample size. Okay, so if I and then so that's it's the mean plus that, or it's the mean minus that. Okay, so if I run lines 13 and 15, we see that the 95% confidence intervals are 147.03 to 152.18. Now before we had 147.02 to 152.19. Right, so they're almost exactly the same, but they're not exactly the same. Why did we not get the exact same answer? And the reason is that, believe it or not, even though I've been telling you that a sample size more than 30 or 60 is big enough, in fact, technically, until you get to an infinitely large sample, there's still going to be a little bit of a difference. So when my sample size is 303, my critical value for t is actually not 1.96. It's a little bit more than 1.96. So how do we find out what that is? And again, this is really just for your additional knowledge. It's impossible, in my experience, no one's ever going to care whether you report 147.02 or 147.03. We never go to that level of precision anyway. But if you wanted to, the function that we would use is qt, and we use 0.975, which is because we use that instead of 0.95 because the idea is that there's two sides to the distribution. Each one has 2.5% of the error, and so we put in 0.975, which I think if you were inventing statistics from scratch starting today, you would not do it this way. You would just say 0.95. But that's how we sort of have done it traditionally. So we ask for the value of qt, 0.975, and we reduce the sample size by 1, which is that small conservative adjustment that I referred to. Okay, so if we run this, we see that the critical value is not 1.96, but actually 1.96785. Okay, so if I go back to the equation in line 13, I've typed it here in line 19, and we run that. So here I've just replaced 1.96 with 1.96785. And now our upper confidence interval is 152.1933. And if we scroll up a little bit, we see 152.1933. The same answer we got from the t-test function in line 11. Okay, so this proves, to my satisfaction at least, that this t.test function will give you the answer you want. And so you don't actually ever need to go to the trouble of doing all of these steps in lines 13, 15, 17, and 19. You're welcome to, but you don't need to. Okay, so I believe that you will find this video to be helpful to you in homework number 4, and that is all for now. Hope that everyone has a good weekend.